to, I was absent
Hi.
for 2 days. I sent you an email. There's a doctor's note
Okay.
to verify that I was indeed sick.
Alrighty. Are you doing okay now?
I'm okay now, thank you.
All right, great.
Thanks. Thank you. Back.
Alrighty, so we are getting started today, and so we're going to continue the discussion of predicate logic, and we'll use certain examples of Prolog. I am not done with the preparation yet, so I can't really run Prolog today. Well, it depends on how much time we have, so maybe we can experiment with Prolog a little bit in today's class. But the point today is to continue the discussion, and we'll talk about predicate logic and actually get to see how it can be used, how it can actually be utilized. So hopefully it will be kind of practical today and relates to programming a little bit, because I know most of you want to get into programming, but not necessarily the math of all this stuff. All right, so we're getting back to predicate logic. And I added quite a bit of stuff to predicate logic inference. It's not done yet. I still have a little bit more to go. But there are certain examples in there already relating to what we have already talked about. So let's go ahead and I'll start with new concepts in predicate logic just to make sure that we got everything done here, and then we can move on. Okay, as it turns out, we are not quite done with that yet. Okay, so the first part is, we want to understand what is considered a well-formed formula in predicate logic. We know how to define that in propositional logic already, but in predicate logic, it's a little bit different, not a whole lot. It's just that everything is now parameterized. Okay, so once you have everything parameterized, then we start with the definition of a predicate, which is like this. A predicate basically is, in mathematical notation, it starts with an uppercase letter, typically P, Q, R, S, and so on. And they have parentheses to surround, individual parameters. So in this case, T1 all the way up to Tn are considered basically parameters, or they can also be seen as what we call terms. Predicates cannot nest. You cannot have a predicate where it has one term that is another predicate. That does not happen. This is also considered a formula, okay, when you have the comparison, the equality comparison of two terms, that can be considered as a formula itself, okay? So T1 equals to T2 is a formula. The negation of a formula is a formula. So the formula itself can be a predicate, can also be a single comparison. If you connect two formulae using a connective, I think we talked about this last time, but it's a good place to start. If you connect two formulae using a connective, which are our disjunction, conjunction, implication, and equivalence, then the result is also a formula. And then the last one is an actual new thing too. It's using the quantifiers. If you use a quantifier on a well-formed formula, it is also, the result is also a well-formed formula. Yep.
For the question mark of the placeholder, does that, when you say connective, you mean like disjunction?
Yeah, conjunction, disjunction, implication, and equivalence.
Okay.
Yep. Okay, so now it all depends on what do we consider as a term, because you can pass a term as a parameter to a predicate and also to the equivalence or the equality check. A term can be defined as follows. It can be an element from the universe which has several names. Okay, you can call that the universe, or you can call that the domain, and also the universe of discourse. Yep.
So if you were talking about cats, for example, would a type of cat, say Siamese cat, would Siamese be a term?
It depends on what you want to do with the system. If you want to have to deal with individual cats as well, then you will have to have, like, individual cat names, as a part of the universe. Okay. So it depends on what you want to deal with. But if you only want to deal with, like, which species is a subspecies of which one, and also, denote, special properties of each species, then you don't need the individual names. Okay. All right. A variable is also a term. The result of a function is a term. Now, this is something that is new in predicate logic, you are allowed to use functions. And in this case, in this sense, a function is just a mapping, but it does have to meet all the requirements of a function, which means everything in the domain has to map to something in the codomain. But in this case, the codomain and the domain are the same set. They are both the universe of discourse in this case. Are there any questions about what is a function? Okay, no questions. And the function can be, can have any number of parameters. Okay, you can have, you can map the Cartesian product of 5 times the universe of discourse and map it to just the universe of discourse. That would be considered a function as well. All right, so this is all the stuff that we have talked about so far, and what we have not gone through would be the second part. So we'll finish this whole section here. Because of the use of quantifiers, there's also a new concept of what we call a free variable as opposed to a bound variable. A free variable is one that is not bound, and bound means it is not free. So that's not going to be very helpful. But what is the definition is a variable is bound when we apply a quantifier to it. In other words, if I just give you a predicate like px here, x is a variable, and in this case it is a free variable. We are not saying anything about x. It is not bound in any particular way to anything. On the other hand, if you add the quantifier there for all x, px, then x as a variable is now bound to the quantifier for all. In other words, every time we talk about px, we are talking about a particular x from the universe of this course. Yep.
Reading that the variable is called first order sentence. Would this be considered a first order sentence?
This will be considered a first order sentence. The second order sentence allowed you to use a predicate as a parameter to another predicate. The first order does not allow that. So there are limitations as to what we can express in first order logic, but it's already expressive enough for most practical use. So you're just reading a little bit ahead of me, that's good. So as it is, predicate logic is useful because we can use it to state formulae, but the usefulness is limited. This is because as it is, we have all the mechanical constructs, but so far there's no meaning associated with the syntax. So at this point, what we have done is to define the syntax. What is considered a well-formed formula in predicate logic? The next section starts to talk about the meaning of predicate logic. In other words, you can have a whole bunch of syntactically correct structure, but if you don't assign any meaning to the syntactical structure, it is still pretty meaningless. It's just like with C and C++, there are certain parts of the language is actually a semantic kind of thing and not a syntax kind of thing. Okay, I'll give you an example. Okay, in C and C++, if I have a function f like this, okay, and inside I will say, okay, int x, and I say return y. Okay. And let's say there are no global variable y whatsoever in this particular program. So this will still be syntactically correct. In other words, if you try to push this program through a syntax checker, the syntax checker will say everything is fine. But what about y? Y is not defined, and we have a local variable x that is not initialized and is not used. Those are the semantics of this program. Okay, so the fact that you can only refer to variables that has been declared in some way before you use it is a semantics. Okay, it is the meaning of the programming language, not the syntax. The syntax only requires this to be an expression that returns. Only needs to be an expression. It does not even have to return the same type as the return type of the function, because that is the meaning. There's a return type here, that's a syntax. There's an expression here, that's a syntax. In other words, if I write this subroutine and simplify everything to this, it would still be syntactically correct. I'm not specifying any return value, but it would still be a valid statement. Is that okay? Is everybody understanding the syntax of something as opposed to the semantics or the meaning of something. Okay, very good. So now we are going to talk about the semantics of predicate logic. Predicate logic has something like the iota set of propositional logic. The iota set of propositional logic are all the WFFs that are true to begin with. So that will start with 1 itself, which is the true statement, the negation of 0, which is also known as true, and so on. So with predicate logic, we also need a mechanism to do about the same thing. So the way we do this is using, guess what? Predicates. Okay, so we're going to use predicates for this purpose. This part here is just a re-explaining of what is considered a domain of discourse, or universe of discourse, or just universe, or just domain. There are multiple names for this particular set, but usually it is using a letter D, okay, because it is also known as the domain, or the domain of discourse. It contains all the elements that are of any particular concern to us with the system that we are trying to make here. With predicate logic, you can have functions. Okay, so this is the explanation that I have been talking about a little bit earlier. You can have functions, and a function can take the Cartesian product of D as many times as you want. Okay, I'm trying to highlight this one here. Okay, there we go. Okay, so in this case, I'm just using n to represent any number. You can take the Cartesian product of D any time you want, including 0, and just map that result to another element in D. Okay, that's a function. Actually, I take it back. It has to be at least 1, but that's the necessity of being a function. The second one is a predicate. Now, when you look at this definition of a particular predicate P, it looks kind of like a function because it is a function, but it is a function with a different codomain. With a regular function, the codomain in predicate logic has to be, D itself, but in this particular case, the codomain is 0 or 1. It is true or false. In other words, it maps any n tuple with elements in the universe of discourse to either true or false. It's basically saying, is it true that blah 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 blah, or is it false that blah 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 blah? Okay. Are there any questions about how a predicate looks like in predicate logic? It's just mapping an n tuple to either true or false. And the collection of all functions and all predicates is known as the interpretation of a particular system, and we usually denote that using M. So M is not really just one function, it's not just one predicate. It is a set of all functions and all predicates that you want to define in a system. Are we still doing okay so far with this stuff here? Okay. So we took a look at this example because last time I just wanted you guys to look at an example first. So in this particular example, we are only concerned about the relationship of these people in terms of ancestry. So that's why the universe of this course, D, is now defined to be just Mary, John, Paul, and so on. So these are 9 people, I think, are the elements of our universe. And then we'll start to define our predicate. The predicate, as we talked about a little bit earlier, is a function that maps a particular Cartesian product of the universe of discourse to either true or false. So in this case, I forgot to fix the note. I should have fixed it. I forgot about it. There should be extra parentheses around John and Paul, and extra parentheses around John and Kenneth here, because we are mapping a 2-tuple to either true or false. I would like to do it now, but it would just be distracting, so I'm going to do it later. Hopefully I will remember to do it. Okay, now. Likewise, Q can be defined similarly. So in this case, we can now define, what about ancestry? If I want to express R as ancestry, it can now be defined recursively. Because we can define ancestry as Okay, we can define x is an ancestor of y if x is either the father of y or x is the mother of y. Okay, so a parent is an ancestor. Or we can define it using z, which is an intermediate variable. So in this case, I'm trying to use z as an intermediate person, where x is a parent of z, and then z is an ancestor of y. So therefore, we can establish the ancestry relationship between x and y. Are we still doing okay at this point? Okay? All right. Okay, so this is basically what we talked about last time, and I just went through this relatively quickly because now we can move on to predicate logic inference. So with inference, we are basically just saying, okay, what type of result can we infer from something else? We talked about inferencing when we first talked about propositional logic. So given a set of premise formulae, now can be empty also, a conclusion can be inferred. So we use that symbol that looks like a T on the side, like this one, to mean infer. In predicate logic, a lot of that stuff still applies, but there are other things that applies as well. If I only give you an expression like this one, now this one is definitely a well-formed formula. Why is it a well-formed formula? Assuming x is a variable and p and q are predicates, this is a well-formed formula. Let's check out why this is a well-formed formula. P is a predicate. A predicate cannot take another predicate as its parameter. But in this case, x is a variable, and it's okay because x is a variable. A variable can be a term, and a term can appear as the parameter of a predicate. So when we look at px, it is okay. It is a well-formed formula. We look at rx, it's basically the same thing. Yep, go ahead.
So when you say you can't have a predicate within a predicate, like so you can't have like say p of r of x?
That's correct.
Okay.
Yep. So when we look at r of x by itself, it's okay too, because x is a variable. We can have a variable as a term to a predicate, and r is a predicate. So when we look at this whole thing, we have a well-formed formula on one side, we have another well-formed formula on the other side, and they are now connected by a connective, which in this case is the implication, and that's okay too, okay, because this is replacing the question mark as the operator, and as a result, p of px implies rx is also a well-formed formula in predicate logic. Okay, so we're going to add something to it. Okay, if this is what you are told, okay, if this is just presented as it is implied that it applies to all x in the universe of this course. Okay, so if I add the quantifier for all x, now x is no longer free. It is now bound to the quantifier for all x. But this, as a result, is also a well-formed formula because we started off with a well-formed formula to begin with, which is this one here. When you add a quantifier on top of a well-formed formula, the result is also well-formed. Okay, are there any questions? Yep.
So once you add the quantifier, the predicate is bound?
The variable x is now bound. Variable x is now bound. It is no longer free.
Will that become important if, or will that become important when we actually go to prove things using predicate logic?
Yes, it is. In fact, when we apply predicate logic using Prolog, which is an implementation of predicate logic, the notion of whether a variable is bound or not becomes important. Any other questions? Those are all pretty good questions.
What happens if
Yep, go ahead.
I know you said like a nesting a predicate within a predicate is not allowed for
Right.
a well-formed formula. What happens if you need to express something a little bit more complex?
Then you have second order predicate logic. Second order logic. This is actually also known as first order logic. Okay. Any other questions? Okay, if there are no other questions, we'll talk about the second one. Okay, so assuming there's an interpretation, remember the interpretation uses M as a symbol, and it is the set of all predicates and all functions of a particular system. So let's say, in this particular interpretation, we have a mapping in a particular predicate. So, okay, let's just look at all the mathematical statements here, because I want you guys to kind of get used to the mathematical notation. A is an element of D means that A is an element of the universe of this course. Okay, it's just an element of the domain. It's one of the things that we're concerned about in this particular logic system. That's the first part. And then the second part states that P as a predicate maps A to true. In other words, PA is known to be true. Okay? All right. So what is the big deal when that is actually part of the interpretation? If that is a part of the interpretation, then we can also conclude that this clause is true as well. There exists X in the universe such that PX is true. Is that making any sense? Because I have at least one element in D, the universe of this course, such that it is true that P of A is true. Well, if I know that there's at least one A such that P of A is true, then I can make that statement. There exists at least one X such that P of X is true. Which is a generalization, because now it is no longer just stating that P of A is true, it's just saying that there's something in this universe such that P of that something is true. Is that okay so far? So these are all inferences to make a conclusion. Starting with this one, I can now infer that this is the result. Okay? I can start with this one and infer that this is the result, because this statement, without any quantifier, is implicitly using the for all. It is implicitly stating for all X, this is true. All right. So are there any questions before we move on to something a little bit more interesting? Any questions? Right. So we'll kind of move forward a little bit. Okay. This one we talked about already. I just kind of verbally described it, so there's nothing new here. This one here is basically saying if you have a well-formed formula and it infers the other one, so if phi infers psi, then it also follows that if this is already an inference rule, and you already know, you state that for all X, it is true that psi is true, then it also infers that for all X, psi is true as well. Okay. In other words, you start with one well-formed formula that uses the for all. You have another well-formed formula that connects two well-formed formulae together. Then you can make a statement about the other one, which did not have the for all symbol after that, or before that. Are there any questions about this? Now remember, whenever we use the infer symbol, it is a syntactical operation. It is not a semantic kind of thing. It's not the same thing as implies, even though it is related. Are there any questions about all of this stuff here? If there are no questions, I'm going to use some Prolog examples after this at this point. And Prolog itself is a hyperlink for those of you who want to kind of get a more formal treatment of the syntax of Prolog. This is this is one of the best documentation of Prolog. It's very terse, but it is actually fairly complete as well. So I'm going to skip. I will skip all the way to the syntax of Prolog, just to show you how simple it is. So we go to this part here. Okay, it's using BNF to describe the syntax of Prolog. How many people know BNF, or have at least come across the term BNF? So BNF is basically, sorry, go ahead. No, yeah. Yeah.
Oh, I don't know anything about it. I've just seen it like written down on a side note somewhere.
Aha. Okay, so BNF is really important, not from the theoretical, mathematical point of view, but from the practical point of view. When you look at the syntax description of most programming languages, MySQL, PHP, C++, and so on, it is usually represented in BNF. Okay, BNF is basically just the initial of two people and form, for the F. All right, so this is what we know as a production rule. A production rule is basically saying a sentence expands to statement part. A statement part expands to a statement, or it expands to a statement part plus a statement after that. Okay. In other words, each line is a syntactical rule. This is a token, okay, and it can expand to this part as a body. Is that okay so far? It's also known as what we call a production, okay, or production rule, if you will. Now, in this case, you can see there's a little bit of not recursion so much, but there's recursion here. Look at this one here. It says a statement part expands to a single statement, or a statement part expands to another statement part and a statement. So what this is really doing is to be able to express that the statement part expands to any number of statements, but at least one. That's all it's saying. Okay. So every time you see the OR symbol, which is this one here, the vertical bar means OR in BNF. And then you look at statement, it expands to an ID equals to an expression that would be equivalent to the equality check that we talked about. And an ID is either a variable or it is a constant. And then we have an expression here. This semicolon is actually required. It is part of the syntax that you need to have a semicolon. And then we look at what an expression is. An expression expands to an operand, or an expression can expand to an expression followed by an operator followed by an operand. So that, once again, it is a repetitive type of expression. It's a repetitive type of syntax. It basically means an expression can be a single operand, or it can be a whole bunch of operands separated by operators. That's basically what it is saying. Okay. There are more concise ways of expressing syntax, but BNF is one of the most well understood one. Well, it's used a lot in programming. What is an operand? An operand expands to an ID, or it can expand to a digit. An ID is A or B, and then a digit is 0 to 9, and then an operator is plus, minus, or multiplication. So that's basically the simple definition of a sentence. And then this one is more complicated because it's using parameterized expansion rules, or parameterized productions, and it's basically doing the same thing as the previous one, except it's saying sentence S expands to sentence S0, and followed by a single comma and sentence underscore R S0S, which is kind of the recursive one, because when you look up what is the recursive definition, it is unique to here. I'm not going to go too much, talk too much about BNF and production rules, but if you get familiarized with this type of syntax, it's also called a meta syntax. Why do you think it's called meta syntax? What is syntax? What does it do in programming? It tells you what is acceptable in a particular programming language, right? So C++ has its own syntax. Why do you think this is called meta syntax? What does the word meta means? M-E-T-A.
It means kind of, but not really.
Sorry?
It means kind of, but not really. Like sort of acting something.
Not exactly. Let's look up the word meta, because it is actually a very useful word in programming. Okay, so meta means after, beyond, to indicate a concept that is an abstraction of another concept. Okay, so the word meta-syntax means it is a more abstract form of syntax because it is used to describe what? It's a syntax used to describe another syntax. So that's why it's called a meta-syntax. Okay, so BNF is a meta-syntax because it is used to describe other syntax. And for those of you who don't believe that Prolog is has a simple syntax, let's look up the syntax of C++. Just look up syntax of C++, basic syntax reference. Okay.
You don't want to look at the C++ standard?
Well, this one. No, I need to. It expands to all of these things. I want one single list. And all of these are only referring to maybe this one.
No, it's just syntax overall.
Overall.
Just say list of C++ syntax.
There's still only basic syntax.
Complete list?
Hmm?
Complete list?
Sorry?
Complete list of C++.
Complete list.
There's nothing.
Quick reference. Okay, maybe the quick reference will be sufficient. Because I want you to see, the complexity of a programming language that you're already.
There's PDF right there.
There probably is a link to the C++ standard. Yeah.
Here we go. And this goes on and on and on. The other way you can also do this is to look for either Bison or YACC, Y-A-C-C, or Bison, B-I-S-O-N, and then look up C++. What do you think is YACC? It's an animal that looks like a bison? Well, actually, it's the other way around. We had YACC first, and then we have bison. Not in terms of evolutionary meaning, but in terms of the acronyms or the name of a program. YACC is known as Yet Another Compiler. Y-A-C-C, not Y-A-K.
Yeah,
Okay?
another compiler.
Yes. Okay. And I know most of you do not believe me, so we'll just go up, look up YACC. And sure enough, it is Yet Another Compiler. So you can now call it a meta compiler, right? Because it is a compiler that makes compilers. The input to YACC is basically a strange form of BNF. Okay, it's kind of the same thing, except you can interleave symbols with operations. You can say parse. Up to this point here, do some processing. Okay, like when you're defining a variable, when you have a declaration of a variable, at some point you can say, okay, I want to add this variable of this type into the symbol table. So you can insert code as you're going through the syntax of a particular construct. So that's YACC, Y-A-C-C. The licensing agreement of YACC is not GPL compatible. So when the GNU Foundation wanted to create its own compiler, it could not use YACC. YACC was not licensed to allow that to happen. And guess what they made? Bison, exactly. So that's why we have Bison and YACC. But Bison is basically, at least originally, another YACC. It's a clone of YACC. Now the term YACC implies something else. Okay, if you just see what I'm highlighting right here, is yet another, which means there were compilers before YACC, except they were not as well known. They were not as widely adopted, and this one is basically the first one that is widely used in computer science. So if you want to write your own programming language and don't want to have to reinvent the entire wheel, the whole thing, you can use YACC or Bison to help you, specify the syntax and make a lot of things a lot easier to deal with. Okay, so, yep. Go
So
ahead.
by doing that, you'd take advantage of, I guess, C's compiler.
Mm-hmm. Okay, this might be a good question if there's a link here.
What are you trying to find?
The Bison file of the C++.
It's on Wikipedia's page.
I guess I'm going a little bit off course, but this is a good reference document already. It basically tells you how the compiler looks at constructs. Except it's not entirely true either, because this one is not needed. Let's just expand which one I'm talking about here. When you look at conditional statement in C and C++, there's really no need to specify else if, because in C, the only thing, well, okay, I know I'm going a little bit off course here, but you guys really should know this. In C and C++, a conditional statement starts with a keyword if. Then the compiler expects a open parenthesis. It expresses an expression. When you see something that is enclosed in square brackets, it's not an HTML element. It is a token. A token is to be expanded to something else. Okay. And then a close parenthesis. Then it expects one single statement here. This is the then statement. Okay, we'll just call it the then statement. The semicolon is not specified here. Then optionally, you can also see a keyword else, and after the keyword else, you will have the else statement. I'm just going to use E statement here, and because these two are tokens, I have to use square brackets to surround them. This is the syntax of the conditional statement in C and C++, and that's how the compiler processes all the statements that you specify here. But then where's else if? There's no else if in C and C++. There's only else and there's only if. So when you have else if, it is actually not a single conditional statement anymore. Every time you use else if, you are having a hierarchical conditional statement, not a flat conditional statement. Is anyone kind of following me or not? I'll give you one example. Okay. If A, okay, then we'll specify B as a statement. Okay, so simple statement here. Else if C, and then we have B. Okay. And let's say else. Okay. So that looks like a single conditional statement that has multiple parts, but that's really not a single conditional statement. Because by the time the compiler processes this else here, it knows this else is corresponding to this if, right? And what do we expect after an else? A single statement, right? So when it is expecting a single statement, it comes across the next if, which is okay, because if is the proper beginning of a particular statement, which is called a conditional statement. So this if is actually starting a nested conditional statement. In other words, it is structurally speaking, it is the same thing as having curly braces to emphasize that this is a nested conditional statement within the outer conditional statement. And that's why when I looked at the syntax description here, go like, that's redundant. There's no need to state that at all, because it's automatically recognized in that particular way. All right. Any questions? Okay, you guys can do your own research, but all I'm saying is Prolog is a simple programming language. The constructs are very simple. Okay, in theory, we have two types of quantifiers, but in Prolog, you don't say for all, you don't say there exist. There are no such thing as quantifiers in Prolog. So the question now is, how do we express stuff in Prolog? I'm going to skip through the first few paragraphs so that we can get to the juicy part, okay? So the juicy part is, how do we state something that belongs to the set M? In other words, how do we express basic facts in the system? If I want to make a Star Wars universe system in Prolog, I would state something like that. Okay, I would use a predicate to indicate that Obi-Wan, which is an element of the universe of discourse, is a Jedi. Okay, is that okay? I would use another one to state, Luke Skywalker is also a Jedi. So when you look at these two, each one is called a clause in Prolog, and the clause in Prolog always ends with a period. Okay, it's just like a sentence, ends with a period. So that's a pretty simple statement. In this case, we are already making certain implications. The first implication is Obi-Wan is an element of the domain or the universe of discourse, and Luke Skywalker is an element of that as well. The convention in prologue is when you're dealing with elements from the universe of discourse, they start with a lowercase letter. So that's why Obi-Wan and Luke Skywalker, they're both starting with a lowercase letter. When you want to deal with predicates, it's the same way. Okay, you know, the name of a predicate usually starts with a lowercase letter as well. Okay, that's a standard. And then we have the two predicates. So that means, you know, this is a part of the set M, and this is also a part of the set M, which is part of the interpretation. All right. So the next thing we want to do, let me just kind of highlight in mathematical terms what we want to say. We want to say that every Jedi should know how to use a lightsaber. Okay? So we have a predicate can use lightsaber to mean that, you know, whatever the variable is, knows how to use a lightsaber. And this is how we want to state it. If X is a Jedi, then it implies that X can use a lightsaber. And that applies for all elements in the universe of this course. Is that okay so far? Okay, let me just kind of check with you guys first. If someone can use a lightsaber, does that imply that person is a Jedi?
No.
No, it does not go backwards, okay? It goes in one direction because I use the right arrow and not the double arrow. Okay, very good. All right. But the way we read it in prologue is the other way around, okay? So is a Jedi implies can use lightsaber, is going in the opposite direction. In other words, this is what we need in order for that to be true. And in prologue, variables start with an uppercase letter. In this case, X is a variable, and so is this one X here. So, yep, go ahead.
Do we have to define X as anything for an
Nope.
intermediate variable?
Nope. Any variable is, by default, if you use uppercase letters in a sentence, it is by default a variable to begin with.
So it's always implied.
It is all implied. In fact, all names that start with an underscore, they are variables as well. An underscore all by itself is a variable.
You start using that.
It's called a anonymous variable. It has no name. All right. So are there any questions at this point? Yep, go ahead.
That symbol in between can use lightsaber and
You mean this one here?
yes.
It's basically translated to implied by. Okay, implied by, which is reading the sentence opposite, right? Because if you want to read this from left to right, on line 1 of this particular sentence, if you read it from left to right, it is saying X can use lightsaber only if A is a Jedi. X is a Jedi. But if you say only if, it is the same thing as implied by, which also means if you read it opposite from right to left, then it becomes X is a Jedi implies X can use a lightsaber. Is that okay? They do things kind of in the opposite way, in terms of direction. So that's why you kind of have to remember to read it, in a backward way. This part, by the way, the part before the colon and the dash minus is called the head of a sentence, and whatever is after that and before the period is called the body of a clause. So we have the head of clause and the body of the clause. Are there any questions about this particular statement? You can see that there's no for all whatsoever in here. That's because for all is implied. Okay? If there's a symbol in the head of a clause, I take it back. If there's a variable in the head of a clause, in this case X, it is implied that we have a for all quantifier applied to that variable. Okay? Are there any questions about this statement? Okay. there are no questions about this statement, we'll go ahead and move on. Okay. So we can use parameters to express relations also. So in this case, we have a slightly more complicated predicate, which has two slots, okay, two parameters. And it is stating ownership of things, okay? So the first item owns the second item. So in this case, Luke Skywalker owns green hat. And in the third sentence, I use another predicate to basically state what a green hack is. Green hack is a lightsaber. Are there any Star Wars fans here? Anyone watches that stuff? No, nobody cares. Okay. Why do you think I call his lightsaber green hack? Look, the green part, has to do with the blade, the color of the blade. Okay, so Luke Skywalker. Well, that too, but it is also a hack. The lightsaber itself, is a hack because according to Wikipedia, okay, not Wikipedia. Now I actually read that stuff. So according to Wikipedia, as I was typing the notes for this class, I have to make sure that all of this stuff is correct, right? According to that, the Empire, it wanted to make sure that the Jedi, there's no chance the Jedi can resurface, so they made it illegal to have people to own the crystal that goes into the lightsaber. So what Luke did was to put a synthesized crystal into his lightsaber, and it behaves differently compared to all other lightsabers.
How so differently? How so differently?
How so? When he extends the blade, it makes a different sound. It makes a cracking sound, and then the swoosh, instead of just like that, with the proper lightsabers. So you guys might want to double check the soundtrack of all the movies and see if that is actually true.
That is true now that I'm thinking
Really?
about it.
Yep.
And the invaders in the end still makes the right
So
sound.
you didn't have a green hack lightsaber until after he lost Anakin, the original lightsaber that Obi-Wan gave.
That is correct. The original one was his father's. Yep.
And it's called a green hack because of that.
Yep. Well, I call it green hack because I have to give it a name. Okay, so the statement to express the ownership of Obi-Wan and his third lightsaber. I actually looked that up too. They're all blue, but this is actually his third one. Okay, the one that he died, quote unquote, died with, is the third one. So it's a blue one, and they call it a blue classic because it is actually of a fairly classic design. Nothing special about it. It's just a blue lightsaber. Okay. So once again, I use owns as a predicate to express that Obi-Wan owns blue classic 3, as a statement, as a predicate that is true. Okay, without any additional owns predicate, what about Luke Skywalker and blue classic 3? If it's not explicitly stated, it is not true. Okay? So that's the thing about predicate logic, or prologue to be more specific, is if it is not stated, if you cannot prove it is true, it is by default not true. It is by default false. Okay? Yep.
But you also have to expressly state, like you have in 3 and 4, that those two things are lightsabers, otherwise they're just nothing.
They are just exactly. The first two predicates is only expressing ownership. So for all we know, green hack can be something like that. Just a
Something to hack with.
something to hack with, exactly. And blue classic 3 can be a musical instrument.
It's a hack.
Yeah. But using statement 3 and 4, now we can say, oh, so it is a lightsaber. Yep.
What is a lightsaber need to come before, if you're trying to do that, does it really matter what order you put them in?
Nope, does not matter at all.
And then also, this is also taking from the fact that before we have that Luke Skywalker and Obi-Wan are Jedi. So this is all this is all one prologue.
This is all one big program. That's correct. Yep. Okay, so now that we have these two, we can try to go ahead and express this one here. Every proper Jedi Knight owns at least one lightsaber. Okay, so how do we express something like this? Now, when we say every proper Jedi Knight owns at least one lightsaber, what is that telling you? At least one. Which quantifier are we supposed to use? For all or there exist?
There exists.
There exist. No, it's there exists because because I don't want any proper Jedi to own every lightsaber there is. Okay, they just have to own at least one. At least one is there exist. Okay, so how do we express that and say that X is a proper Jedi only if he is a Jedi, for he or she is a Jedi, owns a lightsaber. The way we do it is this particular statement here. Well, this is, by the way, the mathematical symbol to mean exactly the same thing. It basically says for all X, and X being an element in that universe, if X is a Jedi, okay, if this is true, and only if this is true we care about the other part. If X is not a Jedi, don't even bother with the rest. Okay? So if X is a Jedi, then we also want the following to be true. Now this is the part where Y is bound to the there exist quantifier. The first one establishes the relationship between X and Y, which means that X is the owner of Y. And the second one states that Y is a lightsaber. So this is how we basically express the same thing. Any proper Jedi in this universe should own at least one lightsaber. Are we doing okay so far with the original English sentence as well as the mathematical sentence?
Yeah.
Okay. Okay. So now we look at the prologue sentence, okay, which is an implementation of predicate logic. Now remember, you have to read it backwards, okay? It means it's a Jedi, and when you specify a comma, it is the same thing as an and, okay? So you don't spell out A-N-D or use ampersand, ampersand. A comma is and. Yep.
So then so X is a proper Jedi
Only if
only if
X is a Jedi.
X is a Jedi and owns a
Lightsaber.
Well, owns a Y, and Y is a lightsaber.
That is correct. Yep, exactly. But what is special about Y, okay, when you look at variable Y, it only exists on the body side of the sentence, but not on the head part of the sentence. Okay? So any variable that only appears on the body side, which is the right-hand side of the colon minus symbol, is basically there exist. Okay, there's an implicit there exist to those variables. Anything on the left-hand side, in this case X, has an implicit for all. Is that okay? All right. So that means we have a way to express there exist, because Y is only appearing in the body of a clause, it is implicitly there exist. And since X is appearing on the head of a clause, it is implicitly for all. So what if I have to express for all on the body side? Okay, there are occasions where that is necessary. And that would come to the next one here. Okay, I want to state that a proper Jedi hates all Siths. Okay, there's the right there. Okay, so how do we express that every proper Jedi hates all Siths? Because now we have a problem. You can try to express it using this clause here, assuming that we have all of these predicates stated already, but it's not going to do the trick, because what this is doing is, because Y implicitly is associated with there exists, so this is really just saying, in order for X to be a proper Jedi, X has to be a Jedi, and there has to exist at least one Sith that X hates. That's it. Just one. Yep.
So then, in this program so far, we have two ways to be a proper Jedi. You either own a lightsaber,
Correct.
or you hate a Sith.
Well, you hate all Siths. Okay, that's the intention. That's why this one is that's why this one has a 1 in it and this one has a 2 in it, so that we can later on define the one without a number as a conjunction of these two. Okay, so we're treating each one individually because it's kind of a big mess if you try to combine all of these at the same time. So I'm going to separate them into different type of predicates, and then we can always merge the predicates using the conjunction. Okay. All right, but this is not working because it is implying there exists. So what we need to do is to make use of the double negation. the double negation is going like this, okay? You can actually use the operator not in Prolog, okay? Now let's take a look at, now hates is easy, okay? Hates is basically just, stating, who hates whom, okay, in this particular universe, okay? So you can say, Obi-Wan hates Vader, okay? That's one clause. So you can state, all the facts using hates, but not hates XY means, you cannot prove, it cannot be shown that X hates Y, then the negation of hates XY is true. Okay? So in this case, someone being Seth tolerant is basically just saying, there exists a Y such that Y is a Seth, and you cannot prove that X hates Y. That is being Seth tolerant. Is you can tolerate somebody X can tolerate at least one Seth and not hate it, him or it, whatever. Is that making any sense so far? The definition of Seth tolerant. Okay. Now Seth tolerant doesn't mean that X must hate no Seths. Okay, it simply means that there has to be at least one Seth that X can tolerate and not hate. Okay. So with that definition of Seth tolerant, now we can say is a proper Jedi 2, to separate it from the previous one, can be defined as such. X is a proper Jedi 2, which is the second requirement of being a proper Jedi, is X is a Jedi to begin with, and it is not the case that X is Seth tolerant. In other words, X is Seth intolerant. Is that okay? So what I have done here is to make use of this particular truth in predicate logic. If you can state that for all x, px is true, then you are really saying the same thing as it is not the case that there exists at least one x, so that it is not the case that p is x is true. So I'm just making use of that. But there's no way to combine the whole thing into one single statement. I have to rely on Seth tolerant as an intermediate predicate in order to make this to work. And it all has to do with variables that only appear in the body side, has an implicit there exists associated with it, and there's no way for me to express there for all on the right hand side. Are we still doing okay so far with all this stuff? Okay. So at this point, let's see. We can go ahead and talk about substitution, which is kind of the mechanism behind Prolog and how it works. Maybe, just maybe, okay, we'll spend some time to see if I can get Prolog to work. So I have Prolog already installed here, I think. Let me see. Maybe not. It's okay, we can go ahead and install it. Maybe not. Let's go find it is installed. SWI Prolog is installed here. That's SWI Prolog. Okay, so let's go ahead and terminate this. It wants me to input all the rules in the file first, and then you can read all the rules in, and then we can make queries. Okay, so we'll go ahead and have a little bit fun here. And this is Star Wars.pl, Prolog, not Pro. And we'll state, well, we'll try it first. Okay, we'll just try out the syntax just to make sure it works. Is a Jedi. So when you state something like this, it is basically saying this is true to begin with. Okay, there's no dependency whatsoever. This is actually just a true predicate. And then we'll have another one is a Jedi. Skywalker. And did you guys know that Skywalker was not the original name that George Lucas thought of? What was the original last name? Starkiller. Yep. That was the original last name that George Lucas came up with, and then somebody said, maybe not. Let's make it Skywalker. Okay, so we go to SWI-PL, which is the Prolog engine, and this is how you read in the file, Star Wars.pl. Okay, so it's all compiled. Okay, so now we can ask questions, okay? So the way you ask a question is like this, okay? Is a Jedi. This is the only thing it knows. But then you can give it a variable x, okay? So this is a query. After you input all the rules and all the clauses and all the every knowledge about this particular universe, then you can ask questions. It is interactive. It is really quite interesting. And then you can press the enter key, and it says x is Obi-Wan, but it doesn't say x is Skywalker. Okay. Now this one, it simply means it says it's true. Okay, there has to be a way to make it recursively find out.
Do you have to, maybe you have to teach it that?
Hmm?
You have to teach it that?
Click another enter.
Enter. Now it only finds the first one. Did I have a title in the file? That's another question. Okay, Control D to get out. Go back to Star Wars. Oh, I have that too. It's supposed to match every single one, but it's not finding the second one. Okay. Well, we'll go ahead and state the ownership. Obi-Wan owns Blue Classic 3. Blue Classic.
White space.
Hmm?
So white space is delimited parameter.
And then Luke owns Luke Skywalker owns Green Pack. All right.
So white space matters though? Or
Hmm?
what?
White space is not important.
Oh, okay.
Yeah, so you can use white space as much as you want. Okay, so now we go back into SWI-PL, prolog, read that file in, starwars.pl, and it has 5 clauses now. We'll go ahead and ask what does Luke Skywalker own, okay? So we say owns Skywalker, oh, there's no auto completion, Luke Skywalker owns something. What does he own? He owns Green Hack. Now, you can also ask, does Luke Skywalker own Blue Classic 3? Okay, because we want to see whether we can find out whether something is true or not, or false in this case. So we can say owns Luke Skywalker, comma, Blue Classic 3. And the answer is false. Okay. Now we can also see if the negation is true. So this is all good. Okay, so far so good, right? So these are just the basic facts. We are not even doing any type of implications. Okay. So now we can start to type the implications. Get out of a prolog, go back to this code here, and now we can say is a proper Jedi 1, okay, because this is the first requirement. X, this is the first time we use a variable, and then we'll say is a Jedi. Okay, let's just do this part first, okay? So in other words, without requiring the ownership of a lightsaber, we'll just say that, a proper Jedi has to be a Jedi to begin with. This is our first implication, okay? The first rule that has any type of implication. So go back into this, read the file in. And now it has 6 clauses. We'll say is a proper Jedi X. Oh, okay. It is actually pretty smart. I forgot about the 1. It says, oh, do you want a correction? Yes, please. And it finds that Obi-Wan is a proper Jedi. I'm pretty sure this is waiting for me to press some key to get the second answer. I just don't know which key it is. Oh, space. That's it. Okay.
Funny how that works. Just press the key.
Well, since I think like a programmer, sometimes I can figure out, what keys to press to do something. Which also means I have thrown away every single user's manual there is for all electronics that I have ever owned. Usually after I unbox it, it's like, oh, manual, don't need it. I can usually either download it or figure out on my own how to use it. And then occasionally I come across something that is properly designed and I cannot figure out how it works.
That's properly designed.
Yes. Yes. Okay, so but this is important because Prolog can figure out all the answers. Okay, when you use a variable in a clause, it will tell you not only whether it is true or not, it will tell you every single element that fits this requirement that will make this predicate true. Yep.
So you can basically build your own universe of discourse.
Exactly.
And then it can just tell you the answers based on what
Exactly.
you want.
And that's why it is so useful. Okay, so now we can say is a lightsaber. Okay, so we are adding that blue classic 3 is a lightsaber. Copy and paste, change it to clean hack here. Clean hack. So
Now we can add it. It's a license.
now we can say, also owns a Y, and the Y is a lightsaber. Okay, only these two parameters.
X and
X
Y.
and Y, right there. Okay. So this is more complex now because now we have a stronger requirement to become a proper Jedi 1, right? Yep.
So these particular groupings can become fairly complex in that they can have multiple variants that are like, or variables rather, that are based on different groupings that they're a part of, and that one particular, like, for instance, is a proper Jedi can be based on, like, let's just say 16 plus or whatever.
Yeah.
Okay.
Yeah, and then you can combine all of those using conjunction later on. Okay? So we'll go ahead and see if this works, okay? Because we still want it to work, even though with the extra requirement, it should still be true. Okay? So, well, we can always add someone who's not a proper Jedi. So name a Jedi who does not own a lightsaber.
Leia
Does not
Skywalker.
exist in this universe.
Leia Skywalker.
Hmm?
Leia Skywalker.
Leia Skywalker.
She's the easiest one.
But is she actually considered a Jedi?
In the extended universe.
In the extended universe.
Oh, it's
she
the
is.
extended universe. Okay.
Yeah.
So what does she use instead? Blaster. Much more direct. Refinement. We don't know any
Diplomacy by
refinement.
fire.
Hmm?
Diplomacy by fire.
Yeah. We want to read in sw.pl. And now we will ask some questions, right? Is a proper Jedi 1? And we'll go for X here first, okay? We'll go for a variable so that Prolog can help me find all proper Jedis, okay? And once again, use a space to proceed to the next one, and that's it, okay? The false is actually applied to Leia, okay? In other words, not everything in this universe are proper Jedis, okay? So now we will ask specifically, what about Leia Skywalker? The answer is false, okay? Which is great, okay? It does identify, okay, what about this? What about this? Who is not a proper Jedi in this universe? Ah. And it simply returns false.
You remember that scene from Willy Wonka and the Chocolate Factory when the guy's playing with the computer?
No.
You don't? You should watch it, because that's what this makes me think of. You're the guy punching things in the computer's not telling you what you want.
Uh-huh. Or Scotty in one of the Star Trek movies, he was talking to the mouse. It's like, why is it not working? All right, so this is all working. Now let's go for the second definition of a proper Jedi, which is that person has to hate all sets. Sits. Yep.
Is there a way to get the Leia Skywalker printout instead of just false?
That's a good question. Well, okay. In order for someone not to be a proper Jedi, there are many things in this universe that will fit this requirement. So I think that's not going to be easy to negate it, find out the negation. So what I'll do is I will start to express who is a Sith here. So we'll have Vader. What about the Emperor? What's his
Palpatine.
name?
Palpatine.
Sidious, right?
Sidious, yeah.
How do you spell Sidious?
S-I-D-I-O-U-S.
S-I-D-I-O-U-S. go. And then we have to express the hate relationship. So hate, Obi-Wan hates Vader. And let's just say that he also hates Luke. Seamless.
Does Obi-Wan really
Yeah, he doesn't hate him.
Does he really hate me?
No, I'll tell you that.
And then we have,
You know,
well, because I want one to be a proper Jedi and the other one not to be, so I'm gonna say Luke Skywalker hates Sidious only. Because the other one, after
Oh,
all,
'cause they have
is his
faith in
father,
him.
right? Okay. All right. So now we have, a proper Jedi 2, okay, which is Obi-Wan, but Luke Skywalker is not a proper Jedi 2 because he only hates one out of the two known sins.
Now we have to add in that condition though.
So, and the rule is a proper Jedi 2 only if X is a Jedi. In fact, if you just kind of read out each sentence from left to right, you will sound like Yoda. Just try it once, you will know. Okay, so this is the improper way. Okay, so I'm gonna go for the improper way first. Okay, which means in order to be a proper Jedi 2, a Jedi only hates at least one Sith, and that's it. So in this case, both Luke and Obi-Wan would qualify, but Leia obviously would not qualify because I have not expressed who she hates, which is a function of time. Nobody's getting that one.
Oh, I got it. Terrible joke.
All right, so we'll say is a proper Jedi 2, okay, because 1 is no longer fun, we'll go with 2. And we'll say, who is a proper Jedi 2? Obi-Wan is 1, Luke Skywalker is 1. And Obi-Wan appeared twice because he hates 2 Siths. So there are 2 ways to prove that Obi-Wan is a proper Jedi 2. Is that okay so far? And that's only because of there exists implication on the right-hand side of the implied by operator. Is that okay?
So there are 2 ways to get to Obi-Wan.
There are 2 ways to prove that Obi-Wan is a proper Jedi 2, and it is saying that there are 2 ways, but it's not instantiating the rest. It's not telling you how it's proving it. Okay, so that is not true because we don't want Luke Skywalker to be a proper Jedi 2 because he does not hate Vader, okay, who is a Sith. So we'll go ahead and fix this and say, oh wait, this is not entirely true because we want it to be not Sith tolerant.
Don't you have to define Sith tolerant?
Yep, we're going to do that. So we'll go ahead and define it here. Sith tolerant X only if, okay?
You said it on the page.
It has to be
Is the Sith one not?
Is the Sith Y and what would it be?
there exists a Sith is a Sith Y such that X does not hate Y.
It's just not hate, isn't it? No, it's hate, you're right.
No, I think that should be right. I mean, go ahead and read this out, from left to right,
Oh.
Yep, go ahead.
I see where it is. Hates Luke Skywalker Sidious. You did define it. Luke Skywalker Sidious hates.
Yeah, but not with Vader.
But then is a proper Jedi would still be true for him.
Okay, so the first question is, is Luke Sith tolerant?
No.
Why not?
Yes, he is.
Because he hates Sidious.
But he likes Vader. He doesn't
He
hate
does
Vader.
not hate Vader, right?
Oh, all. It has to be all. Okay.
Well, because as it is right now, the Y there exists with the Y. Okay, so I only have to find one Sith that Luke Skywalker does not hate. And there's one, right? There's at least one, and that would make him, Sith tolerant. Okay. All right. So we'll go ahead and check this out and see if it works. Okay, SWIPL, in SW. This SW stands for stop work.
We got you.
Okay. Okay, so we want to find out, cisp tolerant X. And it returns false, because we want to specify Luke Skywalker, and it is true. Okay. So if you specify a particular name, it is true, but if you specify a variable, it is returning just false.
Because it's checking.
Because not all elephants are like that.
Well, the true and the false that it's checking, wouldn't it be checking against Vader and against Sidious? And it's only the true would be Sidious, and the false would be Vader.
Maybe. Okay, but here's this is the truth. This is the moment of truth here. No pun intended. Is a proper Jedi 2? Okay, and we want to find out whether Obi-Wan is a proper Jedi first. Okay, so Obi-Wan is a proper Jedi 2 because he hates all the known Siths, and we'll ask whether Luke Skywalker is a proper Jedi 2. Okay. And he's not. Okay, so this is actually working. Yep.
So to test like how Sith tolerant is working, though, you could just put in Sith tolerant Obi-Wan, and it should return two false, or two truths rather.
Nope, it will return a false. If I, you mean this one? So if I supply Obi-Wan here, it just returns false.
So why? So that means that there would. Well, I'm just curious how.
Why with Skywalker it returns a true and a false? Because he hates Sidious.
Right. And
Yeah,
doesn't.
that's the false.
Yeah, and does not hate.
Right. Yep. All right. So are you guys kind of getting a general idea of how this works?
Yeah.
Okay. And you can, and on top of the basic variables or the basic constants, Prolog can also deal with lists. Okay, so you can use square brackets to enclose a list, and it can process a list in an interesting way. It can only get to the head or the rest of the body. That's how it can separate elements of a list. Yep.
So my question is like if you ask if you put in Prolog, like is a proper Sith to parentheses, and then you put a bracket, can you do a list of names, or can you not?
Let's find out.
I'm curious, because like say you only want to check you don't want to check everybody that is part of your universal discourse. You just want to check, let's say 3 people. Then whatever you're giving it, can it use a list instead of just an X or just a name?
I will check that out. We are kind of running out of time today. Okay. Now SWI Prolog is available for all platforms, which means you can download it and make it work in Windows. Okay. So for those of you who want to give it a try, you can just kind of play with it a little bit. I think this will give you a better feel of what predicate logic really is and how it is actually applied in programming. So next time we'll talk about how to implement factorial in Prolog.